Take 5. Okay, so we'll see how it goes. We're gonna look at Green's theorem. Grass is always greener. And paper view, here we go. And I'm not on the right page because it's take 5. Okay, so what Green's theorem is, the story on Green's theorem is it makes certain line integrals easier to calculate. And there's a bunch of applications of Green's theorem. You can go on Google and check that out if you like, or pay real close attention in your physics class. And so anyway, so it makes certain line integrals easier. Which ones doesn't make it easier? It makes the ones easier that come from a simple closed curve. And so we haven't looked at those two we haven't thought about those before. So simple means that it doesn't cross itself. So this is simple. But this one's not simple because it crosses itself. And closed means that it encloses some area. And so this one is closed, but it's not simple because it crosses itself, but it encloses some area. And this one's simple and closed. And so that's what we're going to be looking at for Green's theorem. The other thing about Green's theorem is that when we use it to calculate things, it's going to calculate things in the what the book calls the positive orientation, and that is counterclockwise, as opposed to the negative orientation, which is clockwise. So those two ideas kind of going a little bit. And then this is Green's theorem here, and they say, let C be a positively oriented piecewise smooth curve, piecewise smooth, simple curve on a plane, and let D be a region bounded by C. If P and Q have continuous partial derivatives on an open region that contains D, then this integral here, this is going to be, P will be in terms of x and y, and Q will be in terms of x and y possibly, is equal to, and then you probably recognize those pieces before. So the partial of Q, so it's a double integral there, and we found a lot of double integrals in the previous chapter here. So this is the partial of Q with respect to x, and minus the partial of P with respect to y. And I don't know if you guys are remembering those, but those two things had something to do with being conservative. Do you guys remember that? If they were equal to one another, then the vector field was conservative. Now, one thing I wanted to show you about this, and that's why I left this space here, and I forgot to mention it before when we were kind of going along, but I just wanted to mention just a tiny bit. So I want you guys to recall that in my writing where you can see that this right here was a vector field. Put those. So this was a vector field. This is a vector field. And so just kind of thinking about what we had before. And then we had a vector here. And then just real quick, this was something that we kind of looked at and kind of saw on Thursday in class. Well, I was going to try not to mention any particular days. But if I take the derivative here, this is dr. And then this would be dx I plus dy j. And then just kind of remembering just a little bit, just kind of just putting just part of this together just a little bit. Do you guys remember that when we had the integral, that equaled, do you guys remember what that equaled? This is that guy right there. Yeah, it was work, right? And so if we're just kind of looking at this just for a second here, so what we have right here is this. We have this right here. And so if I put those two things together here, so here is my F is PQ, dotted with, and then dr here, which is dx dy. And if we dot those together, so what this thing is right here, over here, is some type of work. And so that's kind of what we've got going on there. Now I wanted to show you also, so in words, a line integral, so that's what we had up here, a line integral for a simple closed curve, movement in the counterclockwise direction is equal to a double integral over the region that of the curve contains. And then some new notation here, and so an integral with a circle on it, and that is used to indicate a line integral is calculated using a positive orientation. Remember, that meant counterclockwise, and I got that inserted in between there, and I didn't mean to. I meant to put it at the end of a simple closed curve. So this is advertising, that symbol is advertising that it's a simple closed curve, and in the counterclockwise orientation. So we're gonna give a try to an example here, and so they've told us, they've asked us to find this this line integral, and they've over this curve that is this triangle with these vertices here. And so what we want to do is, in order to do this, is that we want to identify P and Q. So this is P, and that is Q right there. And then when we go to look at setting this up, we're going to draw this as well. And so when we set this up, this is some kind of work, remember, so I'm going to call it work, what the heck. This is going to be the integral, and I'm going to put that little do I want to do that? Yeah, what the heck. I'll write this. So this is P dx. Well, trying to decide what work I want to show on this work problem. So this is going to be equal to the double integral, according to Green's theorem, over the region. And remember that it's the partial of Q with respect to X minus the partial of P with respect to Y. And I think I've already mentioned, well, see, this is my 5th time through this video, so I don't know if I've mentioned or not that these were the pieces. Remember that when we were showing something that was conservative, that if they were equal to one another, then it was conservative. So we have this dA. So that's Green's theorem, right? And so I do want to find those pieces. So I've identified P, and so I'm supposed to take the partial with respect to, I want to identify Q, and I want to take the partial with respect to X. So that will be Y. And then identifying P and taking the partial with respect to Y. So taking the partial with respect to Y, that will be 0. So Y minus 0 dA. And then now I'm going to use this to come up with my bounds, and then I'll be in business. So I'm going to draw this. You should always draw it. So here at 0, 0, and then it goes to 1, 1. I'm going to put that right here, 1, 1. So over 1, up 1, and then 0, 1. So this is this triangle here. And we're going around this way, right? So that's kind of the story there. Now, when we go to integrate this, so this is what it's enclosed. So it is a simple closed curve, and we have the choice of doing dy first or doing dx first. You guys remember that story? And here I think it's probably half dozen each to the other. And so I was just kind of thinking that if I did dy first, I would be going from this line, which is surely the line y equals x, to that line right there, which is y equals 1. And that would be just as easy as going this way. If I went here, I would be going from x is 0 to x equals y. And the only reason that I might consider doing that as opposed to the first way is because of the 0, because it makes it just a tiny bit less work, and I'm feeling kind of lazy, and so that's what I'm going to do. So it does not matter though. I don't think that this one is much harder or easier either way. And so if we go this from here to here, we're going across that from x is 0 to x is equal to y, because that's what that line would be right there. And then our y's would go from 0 to 1. And so we have y and then the dx dy. And then we're going to integrate that. And that's what we all, well, we did a whole bunch of those in chapter 15, right? And so when I integrate this, I get xy from 0 to x equals y. I have to write that, otherwise I'm going to mess it up. I probably should be putting the x here too to remind myself what I'm plugging in. And so when I plug in for x, I'm going to get y squared minus 0. And then I want to make sure that I integrate that. So then that's going to be from y equals 0 to 1 of y squared dy, which is y cubed over 3 from 0 to 1, which is 1/3. So anyway, so that's Green's theorem. Green's theorem says that if you're trying to find a certain kind of work, that you can make it into a double integral. We knew how to solve those. So I guess some comments about example 1. This gives us the work done by moving a particle around the triangle one time in the counterclockwise direction. The vector field is, so this is the vector field. So notice here was our vector field, x cubed I, right? And plus xyj, so that's our vector field. And then a comment, I put my finger over the answer. What if we reverse the direction and instead of going in the counterclockwise direction, went in the clockwise direction? And yep, the answer would then be negative 1/3. And so anyway, so we're going to give another try to another one here. This is example 2. And so when I want to find this, 2x dx plus minus 3y dy. And so this is P and that is Q, right? And then oh, and yeah, it said simple closed curve. I was just about to say, got to make sure that you have a simple closed curve, otherwise you can't apply Green's theorem. But then, and then I was like, oh, wait a minute, there it is. I've read about it. It's there. So don't forget that this is equal to the double integral over the region, and it said any simple closed curve here. And so I'm thinking, what the heck how is that gonna turn out? Didn't I have to draw it? Let's see what happens though. So this is equal to this, dA. So in our case, gosh, there's not much room here. I hope you don't write as big as I do. So with Q being equal, here's Q equal to minus 3y, with respect, taking the partial derivative with respect to x, that gives us 0. And looking at this one with respect to y, we get 0, so minus 0 here, dA. And so this is going to equal, yeah, this is going to equal 0. And one of the things that you might be noticing, you might kind of remember here, do you guys remember this story? When these two things were equal to one another, which is just what happened just now, when they were equal to one another, do you remember what kind of curve, not what kind of vector field it was called? Yeah, it was a conservative. And so would every single time I had a conservative vector field on a simple closed curve, because of Green's theorem, every single time I would get for the work 0. Yep, so that's the story. I think some of you already told me that, actually. Okay, so this is example 3, if I can get it in the shot. My tech guy is back today, and so hopefully I won't have that awful screeching that I had on the other video. They were all laughing at me over that, but okay. And so, and now, and things are not upside down. And so I was trying to work with, because I had set it up myself and I had plugged in things a little bit backwards. So I'm probably lucky that it even worked. Okay. And so here they're asking me to find the work, and they've given me this curve, right, this vector field rather, right here. And so when we put this together, I kind of did that at the beginning, right? And so that you can kind of see that it's going to go together the same way that you did. So should I do that again? Why not? This equals this. Oh, that's a y. And then if you take the derivative, dr equals dxi plus dyj. And then this work here, our vector, we got our vector field right here. So I'm going to put that vector field there, x squared y plus x cubed. That's a comma, not a end of the vector. 2xy, and then dotted with, well, dr, well, here's that. So this is dx, dy. And so when we put this together, we get this, which is where they started us on the others. I had forgotten that I had that here too. So now I did it 2 places. Okay, so now this is our situation. If we have a simple closed curve, then we could use Green's theorem. And so you can look over here and you can, if you wanted to make sure, by doing a little drawing of that. And so we have y equals x, and then we have y equals x squared. Why do I do that? I made that one too big. Y equals x squared, right? And so this has enclosed this right here. And so that's is going to be our simple closed curve. They said, I guess, somebody said, assume that the motion is going to go counterclockwise. This right here is at the origin. And what is that point right there? Do you guys know? If it's where y equals x squared and y equals x intersect each other, do you guys agree that would be at 1, 1? Now, I'm not going to spend too much time on that before I make sure that this is not conservative, because if it is conservative, I'm going to get 0 anyway. So this is equal to, and then the double integral according to Green's theorem, right? And should I write this out? That's a partial not drawn very well with respect to y minus the partial of p with respect to x dA over the region right there. I think I'm using R, and I think our book used D, but remember they kind of use both. And so I don't know why I've used R, probably because Professor Leonard used R. And then I noticed that, and I was going to use D, but then, so when I did the homework, I used D, and then now I've forgotten to do it, and here I am using R. Oh well, it'll be all good. Okay, so this is right here is P, and this right here is Q. So if I do the partial here, I'm going to get 2x and minus, and if I do the partial here with respect to, this was respect to y, this one's respect to x. Donna, I think you have that backwards. This should have been with respect to x, and this one should be respect to y. So I should have been taking the partial with respect to x here. So this actually should have been, I did what I said I was going to do, but what I did was wrong. I have to always remind myself that it's backwards than what you would think. You would think it would be the partial with p with respect to x, but it's not. It's backwards of that. And I had been doing pretty good of not writing it wrong until here. I'm not starting the video over for that little boo-boo either. It has to be more of a major boo-boo for me to have to start the video over again. Okay, so here, when I take this partial with respect to y, I'm going to get x squared there. So this is going to be, the minus sign comes from here, minus x squared here with respect to y is just x squared, and with respect to y, that's 0. I had a hard time taking that partial derivative, and it wasn't that hard either. Okay, now I'm going to get my bounds kind of going on here. I have my lovely picture over here, and and I know it said counterclockwise, but maybe I'll put a little arrow on there. And so I have to decide, do I want to do dx or do I want to do dy? And I don't know. The equations are already solved for y, and so that would maybe make it a tiny bit easier to do dy as opposed to doing dx first. But I think it's pretty half dozen each to the other. If I did want to do dx first, I would have to solve these equations for x, which this one would not be hard to solve for x because it's done. But this one I'd get a square root involved. I don't know. I'm going to do dy. I don't think it matters. And so on this one, just like the last one, half dozen each to the other. So I'm going to go from here to here if I'm going to do dy. So I'm first hitting y equals x squared, so y equals x squared. And then the second thing I hit, this is my enclosed curve, is y equals x. And then 0 to 1 are my bounds for x. X equals 0 to x equals 1. And then boom, we're in business. And so that one's pretty easy, not too bad at all. And so let me think about it. I'm taking, I didn't get my dx on there. So I'm taking the integral with respect to y. So this is going to be 2y squared over 2 minus x squared y. 2's cancel out. From y equals x squared to y equals x. So upper bound minus lower bound. So I'm going to be putting in, for y, I'm going to be putting in x. I get x squared. For y, I'm going to be putting in x minus x cubed. Then minus the lower bound. So for y, I'm going to be putting in x squared, which gives x to the fourth. And for y, I'm going to be putting in x to the second. So x to the second times x to the second is x to the fourth. So that's 0. And so I get the integral, and this is going to be my work, x equals 0 to 1 of x to the second minus x to the third dx. And so this is going to be my work. And so that is x to the third over 3 minus x to the fourth over 4 from 0 to 1 equals 1/3 minus 1/4 minus 0. And I'm just going to put that in my calculator is my plan. I think it has something to do with 12 is what I think. So I put it in my calculator and I got 1/12. What did you guys get? And I think I am glad that I gave us the whole page to do that. So what we just found is the work done along this simple closed curve through the vector field and through that vector field, right? So what we've done is what we found was the work done to move a particle along this simple closed curve through one lap around through that vector field is what we just found. So there we go, and it was 1/12. And then I have just one more example. I don't know if I can make that go out there without knocking over my water. Okay. So this last one. So this one is example 4 here, more set up, and definitely a simple closed curve. That's a circle, and so that means this will be equal to the double integral. So I'm not going to write all of that. So this is going to equal the double integral, and right now I'm praying not to write it wrong. So hopefully I did, though. I'm praying to notice when I write it wrong and to correct it. That's more what would be good. So now this is P, and this is, so I'm okay on Green's theorem because that's a simple closed curve. That's our curve right there. And this is our Q. Man, our Q looks nasty. And on this problem here, okay, so when I take the derivative here with respect to x, oh, that's nice because that's gone because it's a constant, right? And so when you take the derivative of constant, you get 0. So we're going to get 6x here. And then when we do this one, we're going to get with respect to y, oh, I didn't realize that. And so now I have 0. So the work is 0. I didn't realize this one was a conservative vector field. I guess I didn't do this one. Is that what I wanted to have on there? Well, that's what I have. It's good. I'm glad. I'll be grateful. Every now and then it's good to be grateful, not to have to work too hard. So my line integral there is 0. So if you'd like more examples than what I've given, and if you want to explore more uses of Green's theorem, Green's theorem can be used for finding areas, as you can kind of imagine. And you can check out Professor L's video if you want, Professor Leonard's video, maybe over Christmas break with some hot chocolate. In fact, maybe I'll have some hot chocolate right now. We bought whipped cream and didn't even use any today. And so this is the video that goes. I think I'm going to put for you guys on your notes all of the rest of the videos that he's made for the rest of the class, and with not only Green's theorem but Stokes' theorem. If you wanted to look at it over Christmas break, it might be fun. Anyway, he's awesome, absolutely awesome. And so I think he is anyway. He'll be telling you head nod if you understand that, and you'll be head nodding. Anyway, okay, so that's Green's theorem. We're going to practice more. Don't worry, friends, and I will see you in the next video.